Hello everyone, welcome back to Technologies Discussion channel. For this video, I'd like to continue the discussion on impedance matching. This video, I will explain and also with an equation help to explain to you why source and load need to be complex conjugate in order to have maximum power transfer. So this is the first objective of this video. Another objective, I want to explain the key difference between maximum power transfer and maximum efficiency. So this will be the second objective for this video. Guys, this is my email. If you have any question regards on this discussion, please drop me an email. Okay, or if not, I actually prefer you guys to send me your question through the comment. Let's start. In AC circuits, okay, so AC circuit simply means higher frequency as compared to DC. Hence, AC circuits is widely used in RF, radio frequency, communication device, and power electronics. And we often say this, we say that maximum power transfer will only happen when the load impedance is actually complex conjugate of the source impedance. This equation explains this. Let's take a look on these two diagrams in order to understand the meaning of complex conjugate. Let's focus on the left first. This is actually the so-called impedance of the source. This is the impedance of the load. Okay, so let's focus on the imaginary number. Okay, so this is the imaginary number. This is also the imaginary number for the load. So complex conjugate means that the magnitude is exactly the same. So when they actually combine, they actually cancel each other. So this is actually the meaning of complex conjugate. They only left the real number. The imaginary number will cancel each other. Let's take a look on this diagram in order to understand better. So now, for example, let's say that the load is actually not the complex conjugate of the source. What you can do is you insert an impedance matching. When you actually insert this impedance matching, when you take a look over here, the input port here, okay, you can design your impedance matching so that the input port have the impedance of a complex conjugate of the source. So in short, you are able to achieve the load, which is actually complex conjugate of the source. And because of this, maximum power transfer actually occur. Let me explain the key difference between maximum power transfer and maximum efficiency. This, in fact, is a very important practical concept. When we actually achieve complex conjugate, we actually want to do maximum power transfer. However, these two things, maximum power transfer and maximum efficiency, does not exist together. When we achieve complex conjugate, for this case here, 50% of the power, in fact, will be lost in the source impedance. This is, in fact, undesired. And because of this, in fact, power engineer actually avoid this complex conjugate unless signal strength at the load is more important than the efficiency. Let's take a look on this further to understand maximum power transfer and maximum efficiency. For maximum power transfer, this condition will only occur when the loads actually receive the highest possible power from the source, which simply means that the load will be able to receive the most possible highest power from the source. Then we can call this maximum power transfer. This will only happen when the load actually become the complex conjugate of the source, which means that the imaginary number actually cancel each other, while the real number, which is the resistor number, they must be the same for the load and the source. Next, in terms of maximum efficiency, this condition simply focus on how to minimize the energy loss. So this will only occur when the resistor of the load, which is many times as compared to the resistor of the source. Let's come to the key ideas. For maximum power transfer, you actually prioritize deliver as much power as possible to the load, even if some power is waste. So in short, the key design purpose is to have maximum power transfer to the load, even sacrifice in terms of some power loss. So efficiency for this case is only around 50%. because half the power will be lost in the source, while another half will simply go to the load. As for maximum efficiency, if you still remember, we want to minimize the loss as much as possible. So therefore, we need the load resistor to be as much bigger as compared to the source. So with this, you almost approach 100%. And in fact, very little will be waste in the source. So this is actually the key difference between maximum power transfer and maximum efficiency. Let's come to the intuition of maximum power transfer and also maximum efficiency. Let's focus on maximum power transfer first. So this maximum power transfer is like pushing as much water as possible to the load through a pipe, even though half of the water will be leaked out. So from here you can see that there are lots of sacrifice, a lot of water leak out, but the key objective is to push as much water as possible to the load. So this is actually for maximum power transfer. As for maximum efficiency, it's actually slightly reversed. Okay, so basically they want to minimize the leak as much as possible, although the flow will be very slow and also very small. So from here, you can see the key difference between these two, maximum power transfer and also maximum efficiency. Next, let me explain when each will be used. For maximum power transfer, it is mainly used in communication system. Why? Okay, because the signal strength matter. Okay, imagine this. When we actually generate a source, a signal, we want to send this signal as much as possible to the load. So therefore, we want to have maximum power transfer. As for maximum efficiency, for example, for the power system, the electrical grid or for the batteries, okay, where wasting the energy is very costly. So therefore, they want to have maximum efficiency. So again, from here, I would like to conclude the discussion, the key difference between maximum power transfer and maximum efficiency. Let me explain what is actually a complex impedance. So in AC, okay, so the impedance actually look in this form here. So basically we have this complex impedance, we have this R. R is actually from the resistance. They actually dissipate the real power. We also have the X, okay, which is the reactance, can be inductor, can be capacitor. So the key objective is to store and also to return the energy. While last but not least, the J term, in fact, is an imaginary unit. So a source, okay, they typically will be looking like this equation here. So basically, this will be the source. How this impedance look like will be by this equation here. Same for the load, okay, by this equation here. One thing I like to highlight, for inductor, it will be a positive reactance. As for capacitor, it will be a negative reactance. Why mismatch will cause inefficiency? So if the load has reactance that does not exactly match the source, okay, which means that the source and the load, okay, the reactants are not exactly the same. There will be some existing reactant left over. So with this, energy keeps logging back and forth between the source and the load. If you still remember, capacitor store the energy and the inductor return the energy. So with some reactants left over, you can imagine that the energy actually keep slogging back between the source and the load. With this, the current and voltage become out of phase. This is undesired. When they are actually out of phase, this simply means that some power will become reactive power. When we actually have this reactive power, we cannot have all the power delivered to the load. Hence, this is undesired. Next, what the complex conjugate actually does. Okay, so in short, what is actually complex conjugate? For example, over here, this is a complex conjugate of the source. You can imagine that the imaginary part will be the reverse part of the source. So keep this in mind. For the source, since it is inductor, so therefore it has a positive reactance portion. And for capacitor, in fact, they will have a negative reactance portion. And basically with this, you can imagine that they will cancel each other. As I explained earlier on, with complex conjugate, okay, as mentioned over here, the total reactant will be equals to 0. This means that the system actually in fact become a very purely resistive. The voltage and current hence will be in phase, and all the power will be delivered to the resistance. So this is a good power factor, which is equals to 1, which is ideal. So this is actually why we want it to be complex conjugate. Next, how to total maximum power transfer. So in terms of the theory, the average power that is actually delivered to the load will be only maximized when the load resistor actually match the source resistor, which means that they are exactly the same, while the reactants in fact need to be cancel each other. With this, the combined condition will be the complex conjugate, and the real load resistor will be exactly the same. Before I continue, guys, this is very important for me. I seek your help by like this video. Guys, it's free and it's just a few seconds. Help me press the like button now. For those who are new to this channel, and if you have learned something from this video, help me by subscribing to this channel and turn on your notification bell. Once again, thank you so much for your strong support. Next, I'm going to explain how to achieve maximum power transfer with equation. So in fact, I need to meet two conditions in order to achieve maximum power transfer. The first condition will be equals to the complex conjugate, as you can see from here. From here, you can see that the reactance of the load must be complex conjugate with the reactance at the source. This is actually the first condition. Let me explain with equation. This is the circuit that I explained early on. This will be my source, my voltage source. This will be my source impedance and also the load impedance. The source impedance, you can see that this is actually the real number, okay, which is the resistor value. This is actually the reactance, which is the inductor. The load is slightly different from the source. Again, you can see that we actually has a real number, which is the resistor value of the load. But somehow this reactance is slightly different. Now, instead of inductor, it's actually a capacitor. How to compute the source impedance and the load impedance is actually shown over here. First thing I need to compute will be the current that is actually flowing in this circuit. How to calculate the current? If I know my source voltage divided by my total impedance, then I will be able to obtain the current that is actually flowing at this circuit. So this is actually my source, which is the voltage source, divided by my total impedance. So this is how I calculate the current that is actually flowing at this circuit. So next, I need to calculate the power that is delivered to RL. So this is the real power that is the key concern to obtain the maximum power transfer. I need to calculate how much power will be able to deliver to RL. How to compute this? If you still remember, to calculate the power is equals to I squared R, the current squared divided by the resistor value here. So the current that is actually flow over here, I have compute early on, okay, which is I1. Okay, so basically this is the resistor value at the RL. So as I mentioned earlier on, I1 is equals to V1 divided by ZS plus ZL over here. So this is actually I1, and keep this in mind, there is actually a square term multiplied by RL. So I actually open up this term here, and this is actually the outcome of the power that is actually delivered to the load resistor RL. So next, in order to find the optimum value, okay, for the maximum power that is actually delivered to the resistor RL, I need to differentiate this with respect to XL. With this, okay, what will be the numbers of this XL in order to achieve maximum power that is actually delivered to the resistor RL here? So this is why I need to do this differentiate. After differentiate this equation, I will have this equation. But before that, let me explain how to do this differentiate first. This is the equation, okay, that I illustrate early on over here. So this is actually the equation here. Remember, I need to differentiate this equation with respect to XL. Okay, so with respect to XL means that this is in fact a constant number. Okay, so this is a constant number. This can be A, so I just let A equals to RS plus RL squared, as you can see from here. So key thing is basically the XL. So how to differentiate this term here? Okay, so basically there is a so-called a pattern here. So basically this C is actually constant. This is the A value. So basically I let this whole thing ZS plus ZL equals to U, as you can see from here. So basically when you actually differentiate this, it actually outcome with this, which is minus 2C constant U divided by A plus U squared. Okay, the whole thing actually squared. So this is actually the outcome after I differentiate this equation. Again, from here, okay, I can break up this thing here. So this is minus, so therefore the final equation become a minus term. 2, okay, so basically the C term, which is the constant, which is V1 squared multiplied by RL, which is here. So this is actually the C term. The U term, which is XS plus XL, as you can see from here. Okay, again, let's come back to here. This whole thing squared. You can see for this whole thing squared. Okay, next will be A term. A is RS plus RL squared. You can see that this is in fact the A term here. Next, this is actually the U term, okay, which is ZS plus UL. And remember, there is a squared term over here, so therefore I have this squared term. So this is how I actually differentiate this equation to generate this outcome here. So next, okay, in order to find my maximum power delivered to RL, okay, I let this differentiate number equals to 0. So this will be equal to 0. So once this is 0, okay, I multiply cross product here. All the constant thing all different. Okay, so basically this is the outcome. Okay, so basically from here, okay, I just move one of the term over, okay, which is the ZS, I just move it over. So XL need to be the complex conjugate of the source. Then I will be able to achieve the maximum value at the resistor RL. So this is actually the first condition. So therefore, like I explained earlier on, with complex conjugate, the first condition meet, which means that my power delivered to the RL will be the maximum. So next will be on the second condition. Okay, so the second condition is RL need to be equals to RS. Keep this in mind, as I mentioned earlier on, the two conditions must be met. So therefore, I need to put this equation 3 into equation 1. Okay, so what is actually equation 3? Equation 3, which is the complex conjugate, I need to put this equation into equation 1. So I will have a new power term that is actually delivered to the load RL, which is illustrated over here. So this is actually a new so-called power that is actually delivered to the RL. Next, again, I need to find the optimum value for PL with respect to RL. So now, okay, what will be the value of RL in order to find the maximum power that is actually delivered to this resistor? How I actually arrive at this differentiate, I leave it to you, okay, but you can see my earlier on example to understand this. Okay, so this is actually the outcome after I differentiate this equation with respect to RL. So next, okay, in order again to find my maximum power, okay, I will let this whole thing equals to 0. So this whole thing will be equal to 0. So I multiply this whole below thing will be disappeared. So whatever that is on top, okay, will be written over here. Okay, so what I need to do is firstly, I will remove away all the common term. I have this B1 squared over here. This is actually a common term. I also have this RS plus RL, as you can see from here. I will be able to remove one of the term over here, RS plus RL. So basically, what left after I remove away the common term will be RS plus RL. Over here, I remove this. I remove away the B1 squared. I left only 2RL. So basically, from here, I can combine here. So basically, will be RS minus RL will be equal to 0. So therefore, I just shift so-called my RS to RL, one of them, either one, to the right. So basically, this is actually the second condition, which means that the resistor of the source must be equal to the resistor at the load. Then I will be able to achieve maximum power transfer. So basically, this is what I mean. In order to achieve maximum power transfer, I need to fulfill two conditions. First, okay, the load reactance must be the complex conjugate of the source. Second, okay, basically the load, okay, the real load, which is the resistor load, must be equals to the source resistance. Then I will be able to achieve maximum power transfer. With this, I'd like to end my discussion. Please help me to like this video and subscribe to this channel. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.